Okay, welcome in online folks. 2 o'clock, welcome back to your favorite class. Yes. Announcements. Homework number 2 is posted. It's gonna be due this Thursday, the beginning of lecture. Make sure to take a look at that. Definitely after today, you should be able to tackle all the homework problems, all right? Your first exam is gonna be in class this Friday. I'll give instructions exactly how the exam is gonna happen. Probably send out those instructions tomorrow morning. The idea, more or less, though, is that you will take the exam virtually. So you'll come to the meeting on Friday a couple minutes before 2 o'clock, get yourself settled. Then 2 o'clock comes around, I'll ask you to turn your camera on from your laptop pointed at your workspace. And then you'll execute the exam sort of in a workspace in front of you where I can kind of see that it's you working on your work, all right? Give you 50 minutes to do the test, and then once you're done with the test, you can have another 10 minutes to turn it in. That's more or less how it's gonna go. I'll give some more exact details about how that's gonna go. I'll send out some document tomorrow about that. Okay, that'll be this Friday. We will have a review session for that exam on Thursday night. If you can make it, great. If not, that's okay. I'm gonna record it and post it to YouTube. So you can use it to study. If you have a little bit of time later on Thursday night, you can do that. Not required, so again, you don't have to come. It's just sort of for your benefit. In that review session, we're gonna go over the practice problems, which I handed out. They're on Canvas right now. I'm like 70% of the way through my handwritten solutions of that review packet. So look for that either later tonight or tomorrow sometime. Looks like I do have a question in the chat. Can anyone else hear Dr. Hart? Uh-oh. Well, you guys in the class, can you hear me? Okay, the people in the class can hear me. Can anyone else hear? I can. No, I think maybe this person just needs to turn their volume on. Arthur, do what all engineers do. Turn it off, turn it back on. It always fixes it. see what you can do, Arthur. If not, good luck. Yeah, you can try to read my lips. How you doing out there? Does that work? Good suggestion there. Okay. Right. So let's pick up where we left off last time. We were talking about how to define a unit vector along a force. So I just want to recap that quick. And then we'll do some problems. Yes. Practice problems, the best. Practice problems are always the best for learning. Okay. So last time, I'll just kind of recap where we were. And we were looking at defining a unit vector along a force. All right. So this is particularly useful in 3D, and we're going to see why that is in a few minutes here. But generally, we would say, if you have some force in 3D, let's just, for now, write it in sort of an algebraic form. If you have a force in 3 dimensions, then that force can be written as the magnitude of that force, which we usually use these vertical brackets to denote the magnitude of that force, multiplied by the unit vector associated with that force direction, which we call lambda. So here's magnitude, and this is your direction. All right. So pictorially, we sort of saw this as something like the following. We have some vector out in space. Here's our f. And we may have a unit vector that's in the direction of that force, which we're calling this lambda. And if that force has a magnitude of, this magnitude of f, then this is a general good definition for how we might define that force in sort of a 3-dimensional space. And we more or less had 2 ways to lay out or sort of define this unit vector in the direction of the force. All right, so we're sort of defining this in 2 ways. All right. Looks like I got another note here. Did we fix it? How are we doing, Arthur? Looks like he's still struggling maybe. All right, we can define this unit vector in two ways. One is with angles between force and x, y, z axes. And we found that generally to be like lambda is cosine theta x I hat plus cosine theta y j hat plus cosine theta z k hat. And the idea there is if we're out in space somewhere, we have our force, and we happen to know the angle that exists between that force and the various axes. This angle here, we call the angle theta x. The angle between the y-axis and the force F, we call theta y. And the angle between the z-axis and the force, we call the angle theta z. All right. So we could define our unit vector lambda using those directional cosines. And you may see this as L, M, and N. And we define then our unit vector if we have those special little guys, which we call our direction cosines. Then we can say that this lambda is simply Li hat plus M j hat plus N k hat. All right, that's our unit vector in the direction of the force, given known angles between the force and the various directions of the coordinate axis. So that is one way which we might define this unit vector lambda. Another method is by defining the unit vector between 2 points in space. So you also might define this unit vector between 2 points in space. Okay. So here we are with x, y, and z. And let's say we have some point here, which is P1. And we have a force that exists between P1 and some other point, P2. And let's say that there is some distance between these guys in the x and the y and the z directions. All right. We call this distance in the x, let's call it dx. The distance in the y, we call dy, and then the distance in the z, we call dz. So if P1 is at location x1, y1, z1, and P2 at location x2, y2, z2, then these general distances between these 2 points we might label as dx, which we say is something like x2 minus x1, the difference between the x points. Our distance that we travel in y is the distance between the y points. And the distance that we travel in z is the distance between the z points. Okay. So if that's the case, then the total distance between those 2 points, you can use the distance formula to figure out. We say that maybe we'll just label this as just regular d. It's the sum of the squares of the individual components. So it's the amount that you travel in x squared plus the amount that you travel in y squared plus the amount that you travel in z squared. All right. So if I go back up to my picture here, that is this length. Right? It's the total distance between those 2 points in space. Okay, I'm not after that total distance, right? What I'm after is a unit vector in the direction of this force. So I'm more or less after, what is this unit vector lambda? That's really what I want, okay? So we showed last time that if you generally know the distances between these 2 points, and you can resolve that, and we showed that the vector lambda is equal to the distance vector between points divided by the total distance between them. All right. So we could define a distance vector from like point 1 to point 2 using the components of the various distances that we have in x, y, and z. So this is sort of in English here, what I've written kind of on the left. But in math, this would be like the distance I travel in x in the I direction, plus the distance I travel in y in the j direction, plus the distance I travel in z in the k direction, normalized by this total distance d. This would give me a unit vector in the direction of that particular force. So this is one other method that we can sort of utilize. And it's sort of this method that we're going to kind of focus in on today. And I will show you why this method is particularly useful. It has a lot of application in sort of real systems and real analysis. And we will look at an example now. Okay. And I sort of brought this example in last time, but I'll actually give you some time to talk and sort of write it down this time. So here we have a tower, and we have a guy wire that's helping to hold the tower in place. One of the wires of the tower is anchored at point A, and we're told that the tension in that wire is 2,500 newtons. I want to determine the components of the force that act on that particular bolt at A, and then I want to know the angles that defines that particular force. So here, this is more or less our force of interest, F. As part of this problem, we're going to define a unit vector in the direction of that force, which we'll call lambda. This will help us sort of define this particular force. Give you another minute or so to copy down. Okay. So let's work through this. We want to find the components of the force in the various directions. Here, that's kind of part A of the problem. And also, sort of for part B of the problem, the angles that this sort of guy wire makes sort of with the coordinate axis. All right, so something that we're given, that the magnitude of that force in this particular wire is 2,500 newtons. So that's nice. We also know locations in space of top and bottom of wire. Okay? So with what we just talked about, defining unit vectors in space with two known points, we can do that here. All right, so I want to get to my force vector F, which we know is the magnitude of F multiplied by a unit vector in the direction of that force. The magnitude of the force I have, so that's sort of nice to know and good. And the location in space of the top and the bottom wire, I will use to help me define this unit vector lambda. Right? That's what I'm sort of after here. Okay. So let's define a new vector. Between points A and B. All right. I'm going to call this distance vector AB with a bar over it. Distance vector AB. All right. This distance vector is just going to be a vector that has some component in x distance-wise, some component in y distance-wise, and some component in z distance-wise. So let's say that this is dx in I, this is dy in j, and this is dz in k. The distance along each one of the general directions make up the full distance vector AB. All right. So let's go back up to my image now and see if we can use the picture to help us define this dx, dy, and dz. All right, so back to my picture here. Here I'm going to, I don't really have a coordinate axis, so it would be useful to sort of define a coordinate axis. Let's go with the traditional coordinate axis that we sort of used in this class, which is x here, y up, and z kind of coming out of the page this direction. So sort of usually how we do it in this class. And now if I think about my distance vector, which is the vector that's moving from A to B, or not to B, I got to think about moving from A to B and how far in each one of the general directions I move. So if I go from A to B, if I think about how far I have to go in the x direction, well, I'm moving a negative 40 to go from A to B. Okay, I'm going backwards 40 meters from A to B. Okay, so here, this dx is negative 40 meters. All right, I'm going backwards to get to B from A. All right. I've got to go, if I'm going from A to B, I've got to go up 80 in the y. So this dy is going to be positive 80 meters. If I think about going from A to B, I've got to move generally this direction in Z to get to point B. So it'll be a positive 30 meters. That's how I'm defining my sort of distance vector to go from point A, which is at the bottom, to point B. It's kind of important to make sure that we're consistent with our directions there. All right. So generally this distance vector AB then will be negative 40 meters I plus 80 meters in J plus that 30 meters in K. All right. Now what I ultimately want is the unit vector that sort of points in that direction. This is going to help me define the direction of the force F. And so remember, a unit vector has a magnitude of 1. So I need to normalize this vector that I've created by the actual total distance between those 2 points. So I want the magnitude of AB, which is like my total distance between the 2 points. Here, that's going to be the sum of the squares of the individual components. Okay. So this is like negative 40 squared plus 80 squared plus 30 squared. Here, units are meters. Okay. So the total distance between points A and B, here, calculate this 94.3 meters. All right. So then a unit vector along AB, which is the same thing as a unit vector along this force, which is the same thing as along this force here of the wire, is whatever the vector is. We know that we have a distance vector that points from A to B. Divided by its magnitude. Okay. This will give me a vector of magnitude 1, generally in the direction of AB. Okay. So I do that here, I will get negative 40 I hat plus 80 J hat plus 30 K hat, all divided by the total distance between the 2 points, which I calculated as 94.3 meters. Here, this top's also in meters. And if I work this out, I can get some unit vector here that is sort of some percentage in each general direction. And I could find this to be negative 0.424 I hat plus 0.848 J hat plus 0.318 K hat. So this is a nice, useful sort of intermediate finding for us in this problem. It is the unit vector that points towards B from A. Okay, I've got to go backwards some amount in I. I've got to go up a pretty good amount in J, and I've got to go forward some amount in K. Right? And if you look at the leading coefficients here, you get an idea for basically what percentage of the total force is in the various directions. So we know that our force has a total magnitude of 2,500 newtons. 84.8% of that total force is in Y. We have 31.8% of that in Z, and we have 42.4% of that in negative I. So we get a general feel for how much this force is acting in each one of the 3 directions. Okay, so finally we can write our force which acts along that same line. I know my magnitude of my force is 2,500 newtons. It's given in the problem. And I'm going to multiply this by my unit vector that's in the direction of that force. Okay, so I do that. And I distribute my 2,500 across all of those different components. I'll have negative 1060I plus 2120J plus 795K. All this has units of newtons. So this is how you might represent the force between A and B, given 2 points between the line of action of that force and the total magnitude of that force in that wire. Back to the original problem, we want the components Fx, Fy, Fz. It's pretty easy to see sort of from our analysis here what those values are. You could sort of see just directly that Fx is negative 1060, Fy is 2120, and Fz is 795, but let's just be explicit about it. The magnitude of the force in the x direction from that wire is negative 1060 newtons. The force in the y direction, 2120 newtons. And the component of the force on that wire in the z direction, 795 newtons. So if we wanted to answer the question very explicitly and very directly, this would, I guess, be the best answer that you could give. Okay. So that's kind of part A of the problem. So part A, check mark. Good for us. Question. The question is, if I gave you something like this on the exam, how would I want the answer? If I gave you a problem that looked like this on the answer, and you gave me this, I would give you full credit. On the exam, I'll be very explicit about sort of what I'm asking for. It'll be, I'll sort of tell you how I want the format. It's like kind of what I do for the homework problems. I say something like, tell me the magnitude of this force. So just give me a number, which is the force. Or write the force in rectangular components. It's like, you know, some number I plus some number J plus some number K, right? Okay, so that's part A of the problem. Let's move on with part B. Where we want to find these angles that the force makes with these various axes. Okay, well, given our unit vector lambda, this is pretty easy to find. One of our definitions of lambda was not only could we define it between two different points, but we could also define it using our direction cosines. So remember we had something like lambda's cosine theta x I hat plus cosine theta y j hat plus cosine theta z k hat. But we've already sort of solved for this. And we know what lambda is already. We have it previously from the problem. So all we need to do is more or less equate the coefficients in front of each one of the vectors. And we're on our way. Okay. So for theta x, you're going to have something like cosine theta x is equal to negative 0.424. Just do the inverse cosine, and you can find your angle theta x. Here's going to be 115 degrees. Okay. I'll just say similar for theta y and theta z. And you could find that same method, theta y is going to be 32 degrees. And theta z, 71.5 degrees. Okay. That's kind of using all the tricks in our tool bag right now. How are we doing on this? Questions on this problem? Thumbs up from the audience. Wow, I got a thumbs up. Any questions from the online world in the chat? I don't know if we still have Arthur or not. Oh, he's still here. Must be able to hear me now. All right, Kanan also gave me a thumbs up. Sweet, man. Now I know how those streamers feel where they're like always getting the donations and the bits and stuff. And you're like, yeah, cool. All right, so where's, yeah, there's no in-person donate button. Where's the donate button? Okay. So that's sort of defining a unit vector along the direction of a force. All right. The last thing I just want to highlight quickly and go over is your 3D particle equilibrium. So we sort of talked about 2D equilibrium already. Now let's just put a cap on 3D equilibrium. It's going to be pretty straightforward following. So let's remember for 2D equilibrium, on a particle, we had that the sum of the forces on that particle had to be equal to 0. That was sort of our mandatory definition. And in 2D, that basically splits to the sum of the forces in the x direction equal to 0, and the sum of the forces in the y direction equal to 0. This is your sort of 2D setup. That's just like this planar sort of statics that we first started with in this class. And we're going to add to this for 3D. I think we can sort of see where this is going. You have the same general idea, is that the sum of the forces that are acting on that particle is equal to 0. But now instead of just 2 independent directions, x and y, we're going to have 3 independent directions. Still have to enforce that the sum of the forces in x equals 0. Still enforce that the sum of the forces in the y is 0. But now we will also enforce that the sum of the forces in z is equal to 0. So this is sort of what it means to be in 3D equilibrium. Okay, so it's kind of like 3 independent equations now instead of 2. So let's look at a problem where we're actually doing a full-blown 3D analysis. And we're going to do a couple of these problems over the next few days. I did put in your notes kind of a problem-solving strategy for these like 3D equilibrium problems. I'll just pull that up here quickly. If you want to sort of make a note that this exists in your notes, might be nice. If you're looking at a three-dimensional equilibrium problem, it's usually a bunch of forces in 3D space that are acting on a particle, something like what you see in the bottom right there. And then I stole this little figure eight from your book. I'm such a thief. Ideally, you create a 3D free body diagram from the space diagram. Then you give yourself an XYZ coordinate system if the problem doesn't already have one. Then you want to establish unit vectors along each one of these particular forces using either those like cosine relationships that we've seen before, or by establishing a unit vector between two different points in space. Okay. Then use your equilibrium relationships to solve. You'll have all the forces in terms of I, J, and K. And so then set all of the I components, add them together, set it equal to 0. All the J components, add them together, set them to 0. All the K components, add them together, set it equal to 0. Little my macaroni and cheese came up and attacked me there. I had mac and cheese for lunch. It was delicious. Never too old for mac and cheese. All right. So that's the general strategy. Come back to this slide if you're kind of stuck on any of those 3D problems. So we're going to tackle this problem next. You've got a 40-pound crate held in equilibrium by a cabling system like you see there. We want to determine the magnitude of the tension force in each particular cable. Sweet. So do your best with that figure. I'll give you a minute here. A couple minutes maybe, because it's going to take a while to maybe define all the dimensions here. Yeah, you're talking about this dimension here? Yeah, this is 8 feet between D and the middle of the point of intersection between B and C. So B and C are at the same height, and that height is 8 feet above this x-axis. This 8 foot is purely in the Z direction, and that 8 feet is common between point B and point C in the Z direction. You know, it's kind of sometimes hard to interpret these 3D images. You will get better at it though. Okay, I'm going to take this picture into the writing pad. And let's do our best. I'm told that this crate here in the problem is 40 pounds. All right. So I want to find tensions in all wires. Okay. I'm also told that this is an equilibrium. I think that's kind of intuitive. All right. So let's attack this problem. All problems usually want to start with a free body diagram. And obviously, in this particular problem, pretty easy to understand that our point of interest is point A. got all these forces that are kind of acting on point A and kind of coming together to have our equilibrium held at A. So here's our free body diagram about point A. And so I'm going to make what is like a spherical cut about point A. So I'm more or less like isolating point A here, and I'm going to be cutting through 4 different cables when I isolate point A. I cut through this cable here, cut through one here, cut through one here, and cut through one here. All right. So when I look at my free body diagram, I'm going to need to include 4 forces that are acting at A. Okay. So here's my point A. Let's put our coordinate system on here straight away. We'll just try to keep to the image as best as we can. So here's X, here's Y, and here is Z. We'll draw our forces in here. The first one here, I'll just label as the tension in wire A. There's no real point to it, but let's just call this T AE, or maybe we label this crate as point E. And we know that this is just generally going to be the weight of the piece, which we're given as 40 pounds. Okay, so I'm just going to put that straight away. I've got this sort of rope acting here on the x-axis. So let's include that particular force. Here, maybe we call this the tension in AD. It's kind of the magnitude of that force. And then we've got these two guys here, it's AC and what is AB, that are acting. We'll do our best to sort of draw those in space as well. So AB kind of acts a little bit backwards, sort of like moving in the negative Z direction slightly. And then we have AC that's kind of like coming out at us a little bit in the positive Z direction. And so here, TAC. Okay. So those are our particular tensions, right? Now, we need to do an analysis, and we know that this is an equilibrium. So since in equilibrium, some of the forces here is going to be equal to 0. And this is more or less how we're going to have to solve this problem. All right. Remember in 3D, this is going to give us like sum of the forces. X equals 0, sum of the forces. Y equals 0, sum of the forces. Z equals 0. And this is a set of 3 independent equations. Okay. And if you notice in our problem here, we actually have 3 unknowns. Tension in AD, tension in AC, and the tension in AB. Okay. So we'll use these 3 equations, sum of the forces X, sum of the forces Y, sum of the forces Z, to give us our tensions in the 3 particular cables. All right. So first, and I think most obviously, is just dealing with, this particular guy right here. So first, my force that exists in AE, I guess is kind of how we're sort of writing this. The force in AE is the tension in AE in sort of this negative Z direction. And we know this to just be the weight of this object, okay, in the negative direction. All right. So generally my force sort of acting between point A and the crate is the weight of the crate, 40 pounds. And this is acting in negative K hat. So here, negative 40 K hat pounds. So that would be sort of like the force vector that exists sort of in that cable that's basically holding up the crate or holding up that block. All right, so that's sort of pretty easy to understand. All right. Also, pretty easy to understand is what's going on with this particular force here. We sort of label this as like force AD. I can see that the entire tension of this particular guy is in just the x direction. So that would be in like the I hat direction. So also, we have that the force that's acting in AD is the tension, TAD, whatever the magnitude of that tension is, generally in the I hat direction. You see that it's like purely in the x direction, so we'll say that that full tension is in the I direction. Okay. We also know that the force AB, if we're sort of representing this guy up here as sort of a force, that the force that's acting at this particular point is the magnitude of that force, which we're calling the tension AB, in the direction of that force, which we're now going to assign a unit vector here, which is lambda AB. All right. So FAB is the tension in AB multiplied by the unit vector that exists in that general direction. So this is the magnitude of my force in that, and sort of in that line, and this is the direction of my force that's acting. All right. Same thing with the force in the rope at AC. It is whatever the tension is in that particular rope, magnitude of that force, and that is in the direction of that rope, lambda AC. So we're going to get these particular unit vectors here and here using our 2-point unit vector method. We'll say find between 2 points. Okay, same with this guy over here. So let's do that. So here, lambda AB. Remember, this is something like the distance in the x direction plus the distance in the y direction plus the distance in z in the k direction, all divided by the magnitude of the distance between the two. Okay, so we need to sort of define what the travel distance is in x, the travel distance is in y, and the travel distance is in z to sort of work through this problem appropriately, defining this unit vector. Right? Go up to my figure here. Here's point B. Here's point A. If I'm arriving at B from A, I have to go backwards 3 in x. I have to go backwards 4 in y. And I have to go up 8 in z. So I'll have here -3 in x, -4 in y, and +8 in z. So if I want to set up my unit vector appropriately here, this will be something like -3i minus 4j plus 8k. Units here are feet. All divided by the magnitude of the distance between these guys. Square root -3 squared plus -4 squared plus 8 squared. Units in the denominator also feet. You can work this out. you'll have a unit vector, this particular guy, negative 0.318 I hat, so back slightly in x, minus 0.424 j hat, backwards slightly in y, plus 0.848 k hat. And this would be my unit vector that points from A to B, lambda AB. Okay. So we'll stop here and we'll pick this example up tomorrow. Thank you for coming. 250